From a modest spyglass crafted by spectacle makers to orbiting observatories sending back images of galaxies billions of light years away, the telescope has rewritten everything we thought we knew about the cosmos. This is the story of how humanity's unquenchable curiosity sparked inventions that shattered the boundaries of sight, unveiling hidden realms and forever changing our understanding of the universe. In less than 5 centuries, we progressed from crude 3-power magnification devices to instruments capable of resolving objects smaller than a football stadium on planets orbiting distant stars. In this episode, we'll trace the telescope's remarkable journey, meet the early pioneers in dusty Dutch workshops, follow each pivotal optical breakthrough, and discover how successive generations of astronomers and engineers pushed the frontiers of what we can see. We'll explore not only refractors and reflectors, but also the adoption of photographic plates, the advent of radio and space-based observatories, and tomorrow's colossal telescopes that promise even more astonishing revelations. Our narrative begins in the Low Countries in 1608. A handful of spectacle makers realized that by combining a convex objective lens with a concave eyepiece, they could create a device that magnified distant objects. The first spyglasses offered barely 3 times magnification, and their images were fuzzy and plagued by optical distortions. Yet the novelty of seeing far-off ships in the harbor, distant church steeples, or mountain tops that once required hours of travel was enough to spark widespread interest. When Hans Lippershey presented his device to the Dutch States General, hoping to secure a patent, he found that similar inventions had already sprung up independently. The idea was too simple to own. Soon, King James I of England was requesting his own perspective glass, while every merchant captain, nobleman, and curious craftsman clamored for the technology. At this early stage, few realized the astronomical potential lurking within those simple lenses. But that changed in 1609, when Galileo Galilei in Padua heard rumors of the spyglass and set to work refining it. Through meticulous trial and error, he lengthened the optical tube, ground lenses of improved curvature, and increased magnification first to 8 times, then to 20 times. With his homemade instruments, Galileo turned his gaze skyward and opened a window onto a world no human had ever seen before. Galileo's first night sky observations in late 1609 revealed the rugged, cratered face of the moon. Where philosophers for centuries had insisted upon perfect celestial spheres, he saw mountains, valleys, and plains, an imperfect landscape eerily reminiscent of Earth's own geology. He then discovered 4 tiny stars orbiting Jupiter, which we now call Io, Europa, Ganymede, and Callisto. Their regular motion shattered the notion of Earth-centered heavenly bodies. Next, he observed that Venus exhibited phases much like our moon, proving that it orbited the Sun, not Earth. These revelations, documented in his 1610 treatise Sidereus Nuncius, or the starry messenger, sent ripples through Europe's intellectual circles. His sketches of lunar topography, star clusters, and planetary moons earned him both acclaim and controversy. The powerful Catholic Church, invested in the Aristotelian and Ptolemaic doctrines, viewed Galileo's heliocentric friendly findings with suspicion. He was summoned to Rome and, in 1633, forced to publicly recant. Yet the genie was out of the bottle. The telescope had proven its power to challenge the very foundations of cosmological belief. Galileo's refracting telescope, while groundbreaking, suffered from chromatic aberration rainbow fringes that blurred the image's edges. The glass lenses also imposed size limitations. Beyond a few inches of aperture, lens sagging and internal impurities made larger refractors impractical. But Isaac Newton realized that mirrors could solve these problems. In 1668, he constructed the first practical reflecting telescope, using a concave metal mirror to gather and focus light. Newton's design eliminated chromatic aberration because all wavelengths of light reflected off the mirror the same way. Although Newton's original mirror was only about 2 inches across, the principle was transformative. Over the next century, mirror technology advanced from speculum metal, a brittle alloy, to improved glass-coated mirrors. William Herschel, a German-born musician turned astronomer, built a series of ever larger reflectors, culminating in his famous 40-inch 40-foot telescope on Slough Hill in England. Herschel used his instrument to compile a catalogue of over 2,400 deep sky objects, nebulae, star clusters, and galaxies, and in 1781 he discovered Uranus, the first planet found since antiquity. By the mid-1800s, the race was on to build larger and more precise reflectors. Stainless glass blanks and silver-coated surfaces allowed telescopes to reach 100-inch apertures by the turn of the 20th century. But these monumental instruments remained tethered to Earth's atmosphere, which distorted incoming light. Atmospheric turbulence blurred images, and certain wavelengths ultraviolet, X-rays, infrared were absorbed entirely. In 1923, Edwin Hubble used the 100-inch Hooker telescope atop Mount Wilson Observatory to measure distances to spiral nebulae using Cepheid variable stars as cosmic yardsticks. His observations showed that these nebulae lay far beyond the Milky Way, revealing that our galaxy was but one island in a vast, expanding universe. This paradigm-shifting discovery cemented the telescope's place as the ultimate tool for unlocking cosmic secrets. Even as ground-based telescopes grew larger, astronomers faced the inescapable reality of atmospheric interference. Adaptive optics, introduced in the late 20th century, began to compensate for real-time air distortions by adjusting deformable mirrors hundreds of times per second. But the ultimate solution lay in smuggling telescopes above the atmosphere altogether. Launched in 1990 aboard the Space Shuttle Discovery, the Hubble Space Telescope transformed astronomy once more. Hubble's 2.4-meter mirror and suite of cameras provided diffraction-limited imaging across ultraviolet, visible, and near-infrared wavelengths. Its iconic image is the Pillars of Creation in the Eagle Nebula, the ultra-deep field, a tiny patch of sky revealing thousands of galaxies, and measurements of distant supernovae leading to the discovery of dark energy changed both science and public perception of the cosmos. Despite an initial mirror-grinding error, corrective optics installed during the first servicing mission restored Hubble's full capabilities. Over the decades, instruments have been upgraded, and Hubble continues to probe the universe's structure, evolution, and rate of expansion. Meanwhile, specialized space telescopes like the Spitze Space Telescope for Infrared, the Chandra X-ray Observatory, and the Fermi Gamma Ray Space Telescope have opened windows onto energetic phenomena from star-forming regions enshrouded in dust to the powerful engines at the hearts of galaxies. The James Webb Space Telescope, launched in December 2021 and operational since mid-2022, represents the next leap. Its 6.5-meter segmented gold-coated mirror and cryogenically cooled instruments are optimized for infrared observations. Webb peers further back in time than any previous telescope, capturing light from the universe's first galaxies and stars that formed within a few 100 million years of the Big Bang. It also carries spectrographs capable of analyzing exoplanet atmospheres for water vapor, methane, and other biomarkers, bringing us closer to answering whether life exists beyond Earth. On the ground, gargantuan observatories are under construction. The European Extremely Large Telescope in Chile will boast a 39-meter primary mirror composed of 798 hexagonal segments. The 30-meter telescope, planned for Hawaii, and the giant Magellan Telescope, under construction in the Atacama Desert, will push optical and near-infrared resolution to unparalleled levels. These observatories, equipped with next-generation adaptive optics, promise to directly image exoplanets and study stellar populations in distant galaxies with unprecedented clarity. Across the electromagnetic spectrum, radio astronomy has its own storied ascent. In 1933, Carl Jansky first detected radio waves emanating from the Milky Way. Over time, dish arrays like the 100-meter Green Bank Telescope, the Very Large Array in New Mexico, and the Atacama Large Millimeter, Sub-Millimeter Array in Chile have unraveled cold molecular clouds, mapped neutral hydrogen across cosmic time, and even imaged the shadow of a supermassive black hole in the galaxy M87. Tomorrow, the Square Kilometre Array, spanning South Africa and Australia, will combine thousands of dishes to probe the dark ages of the universe and test fundamental physics. Why does this matter? Every leap in telescope technology has fundamentally altered our worldview. The shift from geocentrism to heliocentrism ignited scientific revolutions. The discovery of galaxies expanded our cosmic address. Dark energies reveal forced us to reconceive gravity and the universe's fate. Telescopes drive technological innovation, precision optics, sensors, adaptive control systems, and data processing algorithms. They inspire generations of scientists, educators, and enthusiasts, reminding us that exploration and discovery are defining human traits. Telescopes also bridge cultures and nations. International collaborations power the largest observatories, and open data policies allow researchers worldwide to mine terabytes of imagery. Amateur astronomers contribute by monitoring variable stars, discovering comets, and providing rapid follow-up observations for transient events like supernovae and gamma-ray bursts. From a handheld spyglass in a 17th century Dutch workshop to Webb's GoldenEye orbiting a million miles from Earth, the telescope revolution has been a breathtaking saga of ingenuity, perseverance, and wonder. And the story is far from over. As radio arrays grow in complexity, adaptive optics become routine, and space-based observatories branch into ultraviolet and X-ray regimes, the next generation of telescopes will peel back layers of the universe we can only dream about today. So the next time you look up at the night sky, remember that every point of light has a story, and behind each story stands an instrument born of human curiosity. If you found this journey through optics and innovation illuminating, subscribe and ring the bell for more deep dives into history's greatest scientific breakthroughs. In our next episode, we'll explore the centuries-long quest to transform base metals into gold, alchemy's hidden legacy in the rise of modern chemistry. Leave a comment below. Which telescope moment fascinates you most, and what cosmic mystery do you hope we'll solve next?